So we are very happy to have Frédéric here, and he's an expert in neuroergonomics. So he has many publications about workload and aerospace, working with pilots and all this stuff. So it's super interesting to have him here. And he will also show us how to make a brain computer interface easier to use, which is of course super important to use it in these environments. So very happy to have you here. Please go ahead.
Thank you very much, Christophe, for the introduction and for the invitation. So you can see here from my accent that I'm from France, so Southwest. I'm the leader of the Neuroergonomics Center. Like, we are 20 people with a background in neuroscience, signal processing, and AI. And our main topic of interest is to implement neurotechnology, out of the lab for real-world application. We have a special focus on end-user related issues. And you saw several nice videos from Ivan's group and other groups. And what you can see from SSVP, it works from the bright side, it works pretty nice. You can go with high number of classes as demonstrated by Ivan. But from the dark side, I would say that's, as long as you consider SSVP, it can take like 40 minutes to calibrate the BCI, especially with this type of BCI. And you have to redo the calibration each time you want to use the BCI. Mostly, there's no idle states, meaning that when you don't look at the BCI anyway will output some commands, which can be critical if you think about aerospace application, for instance. It's not self-paced. Usually it's fixed decoding time. And as you can see, researchers are using like LEDs or there is straining on the eye stimuli, so that at the end you can experience visual fatigue, headaches, and in the worst case scenario, epileptic seizures. And as you can see again in this video, the thing is, all these flashes, sorry, I have to move the bar, I don't know where. You are dealing with peripheral distractions because you have all these flashes flashing at the same time. And if you're dealing with patients, it's impossible for patients to focus on one specific stimuli. So in my research group, we wanted to design what we call invisible BCI, meaning that we want to design visually comfortable flickers in calibration that lasts less than 1 minute, and to go with dry or semi-dry EEG system. So let's go with visually comfortable stimuli. So probably if you ask you how many flickers do you see here, your answer will be like 1, 2, and 3. But in fact, there is the fourth elusive flickers that you don't see. And the reason is that it is presented at above 60 Hertz. And if you don't believe me, you see that my colleague will place the photodiode here, and you can see the 65 Hertz oscillation here. So you don't see it flickering, but can you measure it? So with one of my postdocs, Simon Ladouce, we did a frequency stripping study starting from 8 Hertz to 60 Hertz, 62 Hertz with SSVP. And on the y-axis, what you can get is the signal-to-noise ratio. And as you see, from 12 to 20 kind of frequency, you get the best signal-to-noise ratio. This is why everybody's using this frequency. And we also ask our participants to rate their subjective comfort. And you have a nice linear trends, meaning higher frequency leads to better visual comfort, as measured on the visual cortex. And as you can see here, still on between 50 and 60 Hertz, we can still get some signal. But it is at the group level, average over all trials, and can we do single trial accuracy using high frequency flicker? So if you go from 10 to 20, got a nice accuracy. From 20 to 30, the accuracy is still good. 30 to 40, you can still use it. But after 40 Hertz, and especially between 50 and 60 Hertz, the accuracy, single trial accuracy is very low. So, you cannot implement a high frequency flicker for BCI. The second approach we've been trying to go for was to play with amplitude depth reduction, meaning that when, as Ivan showed, usually people go from white to black, which is maximal contrast. Can we go between 0 and 50, for instance? So it looks like this. So as you can see, it's more visually comfortable. Or can you go between 0 and 30, even more comfortable? So we ran a second study in this paper, starting from full amplitude flickers, like very straining on the eye, to 30%. And what you can see here, you can reduce the amplitude depth, until 50% or even 40% without impacting the classification accuracy. So you have more visually comfortable stimuli and still you get a good accuracy. It's only when you pass this 30% of amplitude depth reduction that you start decreasing the accuracy. And then to compare all these conditions, what we did is we implemented an online T9 SSVP-based BCI. So you know how it works. People were supposed to look at 5017, for instance. What you can see here on the left is the reference condition, the condition that everybody is using, like high amplitude, low frequency flickers, and the accuracy is super good. And this is what we get if you reduce the amplitude depth. This is our approach. So you have the same accuracy, but if you play with high frequency flickers, you see that the accuracy is very bad, especially for most of the participants. And if you look again also in terms of visual comfort, you see that our participants reported the same level of visual comfort playing with high frequency flicker or reducing the amplitude depth. So it seems to be like a very good approach. And by using this amplitude depth reduction, it paves the way for the implementation of passive BCI. Because as you probably know, SSVP response is highly modulated by attention. The more you pay attention to your flicker, the stronger your brain response will be. And the objective of this experiment was to see whether we could do almost invisible flicker and still be able to detect participants' brain response. So it was a project funded by Airbus, and they are very concerned with fluctuation of attention with the pilots. So we implemented this Mackworth clock paradigm. I don't know if you're familiar with this very boring task. So you're supposed to supervise this red dot that goes from one position to another. And from time to time, it will skip a position. And then you will have to press the space bar. The thing is, the task lasts forever, like 45 minutes, 1 hour. So you're more likely to experience a fluctuation of attention. And then what we did was to place an elusive flicker at 14 Hertz, displayed on top, on overlay on the screen, presented at 10%. So it's invisible for the user. And what we're expecting is that when the participant will be engaged in the task, we will decode strong brain response. And when the participant will disengage, there will be an attenuation of the brain response as an indicator of attentional lapse. To do this, we developed the Flicker on Top application. It's available on GitHub. So you can present up to 40 flickers at the same time. You can use different colors, textures, SSVP, code VP. You can stream all the flickers on LSL. And the beauty is that you can put them on overlay on any kind of application. So it could be a video game, it could be Word, it could be whatsoever. But you can place them on overlay. And that's what we did. And this is experimental paradigm. So we had two conditions. So the first one was without flicker. So there was a skip. So we had one condition without flicker, one condition with flicker. And you see that the flicker is flashing, but you don't see it. I can show it again. So without flicker, so you see the skip. And now with the flicker, you don't see it. Okay? And we wanted to have these two conditions because we wanted to make sure that our participants were not distracted by the flicker. And this is what we get. This is the subjective rating from the participants. So having the flicker or not didn't affect sleepiness, didn't affect fatigue, didn't affect eye strain, and didn't affect perceived workload. And basically, our participants were unable to tell us whether they had the flicker condition or the no flicker condition. But still, we could measure the 14 Hertz response to the stimulation, which is kind of cool. We had 16 participants. I only display 4 participants, but it stands true for all our participants. What you can see in blue is the signal-to-noise ratio to the 14 Hertz, okay, for this participant and the others. So which is nice is we have kind of continuous indication of, what you can see is clearly fluctuation of attention as measured by the SNR. So you can see that from time to time, our participants are very focused. From other time, they start to disengage, probably like your experience at the moment. From time to time, you are listening to me and then you disengage. I hope not. Anyway, but what you see, so this is fluctuation of attention. The dotted line is the mean of the SNR, and red cross represent an attentional lapse. What is interesting here for this participant, but it stands true for all our participants, when you experience an attentional lapse, it's always when you have a very, very low SNR. And if you do some stats, we can go 1 second before a decision, like before pressing the space bar, and you can see that there's strong statistical evidences that the brain response is different when you have hits and misses, and you have a really big Cohen's d size effect. We look to alpha, theta, or the metrics. We don't have similar difference. We have no statistical differences. So it looks like using this transparent probe, we can at some point predict participants' fluctuation of attention. And also it's interesting because you can go back in time up to 10 seconds before an error. You can still discriminate whether they're going to miss the target. Okay, so just to show you that we can use this flicker for passive BCI. The thing is, we're using this flash with amplitude depth reduction, but it was not working very well with dry EEG. And also SSVP, the calibration can be a burden, very long. And so we also had to improve the stimuli. So now you know everything about code VP. I cannot highly recommend this paper enough. It should be your Bible for code VP. And also one of the authors is Jordi and Victor from Medusa. These two guys are doing really great research, especially Jordi Tillen with the zero calibration for code VP, which paved the way for really end-user friendly BCI. I think you have a presentation, Jordi, maybe about this topic. Yeah, when is it? Stay tuned. So the thing is, we wanted also at some point to improve this M-sequence code. My background is neuroscience. And you see when you have M-sequence, since it's quite fast, you have some overlaps between responses. And they are not necessarily consistent over time. So we adapt this paradigm. It's between code VP and TVEP. And the idea is to play with aperiodic flashes. So we have 3 brief flashes per second. It's not periodic, it's aperiodic. So roughly 300 milliseconds plus a jitter. And why we did that is because when you have a brief flash, we know from neuroscience that it will evoke a very, very strong ERP. And if you compare the ERP that you can get from the burst, brief flashes, and M-sequence, you see that you double the amplitude. So you get stronger brain response, which is very important if you want to deal with dry EEG. Okay? And the way it works, so you have a father code, mother code, and as explained by Ivan at some point, we have like this code, the other code, and we have so they are presented in an interleaved way, meaning that when there is a flash, there's only one flash at a time. Okay? So this is the way we maximize anti-correlation between code. So how it works, so what's under the hood? So you have the raw EEG signal. Back in the days, we were using CNN. And basically, we try to detect whether there is a flash, or there is no flash. Okay, so it's bitwise decoding. We accumulate it. We accumulate more windows. 0, another 1. And since we have enough bits of information, we can start doing some prediction. So prediction is basically correlation. And we see that 1, 0, 0, 1, it looks like this one. But we need more information to confirm. So correlations start to increase. Then when we pass the threshold, we decided to go for the first target. So the next thing is, if you think about in terms of calibration, you just need to learn 1 and 0. Okay, whether there's a flash, whether there is no flash, it's all you need to learn. So we just need 40 seconds of data to train the BCI, and then using correlation, we do kind of code reconstruction. Jordi is doing also as well. And just to want to show you that we have a nice mapping between the stimulation. So in blue, you have the flashes, and in green, you have the ERP. So you have a very nice matching between your stimulation and the response that you decode on the back of the brain. Also, you probably saw that g.tec was using textures. We took inspiration from NextMind and other papers showing that if you use textures, it's already more visually comfortable. But if you have contrasted textures, you really boost the visual pathway responses. So I can explain that very briefly. So basically, the FOVEA is an edge detector. So I'm very good at detecting edges, like my computer edges, face it, and so on. So by presented edges, you will maximize the excitability of the neurons in the FOVEA. Also, we are using random orientation because you know that from visual cortex, some visual population of neurons respond for this orientation, and so on and so on. So by having a lot of randomness and a lot of orientation, you maximize the brain response over the visual cortex. Okay. We had a collaboration with Pierre Clisson with TimeFlux. So we use the dry EEG system. This is the architecture of the BCI. You can download it on GitHub. And if you want to look at the accuracy, so we compare the accuracy of plane versus Gabor type of texture, Ricoeur-based textures. And the accuracy is almost perfect with the Ricoeur and Gabor, and very bad not that good with plane, with high variance. And the reason and selection time was 1.68 seconds, so quite fast as well. And the reason it works so well is because if you have plane stimuli, you have this nice typical P1 response. But with Gabor and Ricoeur, since it's more complex, we have more complex responses as well. So N1, P2, with 3 times the amplitude compared to the plane stimuli. So you really boost the brain response. So I'm going to show you a video. So Jules is my student, PhD student. So you see the calibration. So we just flash. You can barely see the flashes. It's visually comfortable. So they look like this. And you see the signal quality is not that good. So we're just learning 0 and 1. 0 and 1, sorry. And you'll see that you barely don't see the flashes. So the participant's supposed to type this sequence, 6652. And what I want to illustrate is that with this approach, we have a gating mechanism. So when you don't look at the BCI, it doesn't output. You don't get any output. So Jules, we stop looking at the screen, you don't have any output. So you have a natural gating mechanism with this approach. Okay. Also, I want to illustrate that it's super duper robust to artifact. For some reason, you can't hear anything. But so it's a quick task. We're supposed to look at the second one. That will be a blue circle. It's good. Participants supposed to look at the second one. Now this one, that one, sorry. And we are in aircraft. Okay, with clean engines, you have a lot of electromagnetic contamination with such environments. And still we can operate the BCI with a dry EEG system, which shows strong robustness. And so to give you a better understanding of what's under the hood of this BCI, so Jules did this also. So what is nice here, you can see the ERP responses evoked by the flashes. So here in this case, we're using semi-dry technology, which is a good compromise between wet and dry EEG system. And you have like super duper nice ERP, -20, +5, +10. So this is the response to the flashes, the response to no flashes. Look at the scale. So it also gives us some kind of, we have an explainable BCI by having this kind of feedback for the BCI designer, which is kind of interesting. So we better understand why with some participant it works, with some other it doesn't work. It could not work that well, I would say. And now you see the correlation plot. When the participant looking at the targets, you can see the decision algorithm, the correlation. So we're using a momentum decay, so moving average way to to predict the target. So the participant is looking randomly to target, and then we will look at the right target. Okay, so you see it's very fast, and we have nice feedback to understand what's under the hood. If you're interested in to learn more about how we can use feedback to improve human BCI interaction, Jules Gomel will give a talk in session 1, Advanced BCI. Also, the last thing I wanted to show you is that we can use these flashes, texture passive flashes, for passive BCI. with a periodic flicker. So I don't know if you're familiar with this task. It's designed by NASA for pilot selection. Roughly, you have to respond to radio communication, respond to visual alarms, and maintain the crosshair in the middle. It's very challenging. So what we did is we used the flicker on top application and placed some flickers here on overlay, same in the flight simulator, with time flux as well. And the idea is to use this correlation index to see how much attention you pay to the different displays. Okay, so the correlation index that you saw in the previous video as an input. And you see that we are doing this in this task. The flickers are almost invisible, sorry, and you can see the output of the BCI that tells us how much attention you pay to the different displays. So the idea is to go beyond what you can get from eye tracking, because fixation time doesn't guarantee that you're paying attention to something, but using the brain response, how much your brain resonates with the stimulation, we can get an estimate of how much attention you pay to some stimuli. And this is in the cockpit, same things. And the idea is to merge eye tracking and Code VP PCI. Okay, so it's a project with the Netherlands and Jorditelen.
NASA 504, NASA 504.
And now we are using Unreal to implement this using VR. So it's a shell game. The ball will go here. Sorry. So it's just a prototype, we're just working on it. And you see the flashes. And then my student can interact with the VR environment. Okay, so I would like to thank my team. Also, I would like to advertise, because we have started a year ago the Anity Prize. So any papers related to AI applied to neuroscience, you have a decent money prize. And the only thing you need to do is to publish a paper in Frontiers in Neuroergonomics, which is my journal. I'm the co-chief editor of Frontiers in Neuroergonomics. So yeah, feel free to submit any neuroscience AI paper. Thank you very much.
Just keep it on. You sure? Thank you very much. Any questions for Frédéric? Yes, one.
So
let's repeat it for Zoom. The question is if the calibration has to be repeated again and again for every user.
Yeah, so it's a very good question. So what we're doing at the moment with another PhD student who is doing transfer learning, so as to learn data from others and see who could be the good donors, the good receivers. So we're working on it. Still some work to do. But it looks like you still need a bit of training. Jorditelen proposed to do zero calibration, so you should look at his paper, definitely. So something we are looking at the moment. But the thing is, what we discover is the more you use the BCI, the less calibration data you need. Like for me, 10 seconds of data is enough to calibrate the BCI. So there is a part of training that can be involved. But yeah, still need to do a bit of calibration.
Any other question? Did you also do zero-G flights in your studies?
No, not yet.
Not yet?
But something we'd like to go.
Need a subject. Like
yeah. But we operate airplanes in my university, so we're doing a lot of tests in a real flight condition.
Very good. Thank you very much for the keynote.
Thank you very much.
It's very interesting.